Good morning. Welcome everyone to the Congress Hall A of the Data Science Conference Europe 23. My name is Ivana Milenkovic and I will be your host today. I would like to welcome you on behalf of the organizing team of Data Science Conference 23, and we are happy that you're joining us at the biggest AI event in Europe. We can start our first session. Petar Zecevic, Senior Principal Consultant at Poslovna Inteligencija, who is our bronze partner, will walk us through ML in production on Databricks, dive into the complexities of deploying ML models in real-world scenarios, exploring the challenges of model deployment and monitoring. Petar will share best practices, particularly focusing on leveraging the Databricks platform to streamline these processes. Get ready for a comprehensive insight into handling machine learning in production environment. We are impatient to hear you, Mr. Zecevic.
Thank you. Thank you all for coming. So my name is Petar Zecevic. I will talk to you about machine learning on Databricks. So first I'll start with going through why productionizing machine learning is hard and what are some challenges there. Then we'll go through some best practices when doing machine learning in production, and finally go through the features of Databricks that can help with these things. So a naive image that we might have about machine learning, doing machine learning, is that we do some import of the data, doing some ETL into some kind of database. Then we do some feature engineering, prepare data, train our models, validate them, and once we're satisfied with the version, we put those in production somewhere on some environment, and we get some benefits from using our models in production, right? However, there's a bunch of things that we might want to consider, such as is the data streaming or not? What happens if the data, we need to use streaming data? Is the data fresh or is it high quality? What do we do when the schema changes? Not if, but when. Are we versioning our ETL code? Are we testing our ETL code? How do we manage for monitor for distribution of the input data? Do we monitor if that changes or not? Then do we version and test the feature engineering code? Are the features really needed? Do we test for cost of the features? So do we keep track of which exact data was used for training and which model parameters and algorithms we used, which ones we tried out and or not? Do we integration test the whole pipeline? Which environment are we deploying on? Can we deploy, how many environments do we have? Do we have development, testing, and so on? Can we reproduce environment easily? And do we have, if we are calculating our features in production, are they equivalent to the ones that were used for training? And finally, are we monitoring the performance of our models in production? So there's a lot of different things that we might consider here. It's becoming more complicated than the naive version, right? So there's this paper from Google back in 2017, ML Test Score. They tried to create this, let's say, checklist for how to check if your model, machine learning system is ready for production, or if you have any technical debt. So for traditional system development, software development, we have unit tests, integration tests, and system monitoring. This is their figure from this paper. But for machine learning, we have, on top of this, we have machine learning infrastructure tests, model tests, data tests, data skew tests, data monitoring, and model prediction monitoring. And another seminal paper from Google from 2014. The famous figure from that paper shows that actually the fraction of the actual machine learning code that's used for training and testing the models, the development of model code, is actually just a tiny fraction of everything that needs to go into developing and using machine learning models. So there's this emerging field or methodology called MLOps. There are different definitions of this, but we can say that it consists of DevOps, DataOps, and ModelOps. So DevOps comes from traditional software engineering. It deals with application code versioning, continuous integration, where we integrate small changes in the code base into the final product frequently. And we do the same with deployment. We deploy these versions frequently. And to do this, we need probably automated testing and infrastructure as code, automated deployment. And of course, configuration management is very important, and monitoring of applications in production. So this is all traditional, well-known stuff. There's also data ops that we have to do ETL, some transformation of the data processing pipelines. And we also need to do code versioning of this code. We need to keep track of data lineage to see where the data came from. I mean, this is the actual best practice, to keep data lineage. Keep track of where the data came from, where it's being used. And data testing, of course, for quality of data, some ranges of the data, amount of missing data, and things like that. Data privacy with all the regulations, GDPR, and that's also very important. Data self-service, we want to allow our users, our departments to use data autonomously on their own. And finally, feature engineering, creating data as input for our models, which is also something that ModelOps also deals with. ModelOps deals with everything regarding models, of course. We need to track our experiments, do validation and testing, versioning of model code, and deployment or apply models to real-life data. And finally, monitor for performance. So on top of all of this, we have also different paradigms. We have regarding the velocity of the data. Most of the applications are batch, so that's like in latencies like in minutes. Streaming in seconds, real time in less than a second, let's say, typically. And we have these specially tuned models that go onto edge devices, on mobile devices that are trimmed down and specially tuned. So let's go through some of the best practices when doing machine learning and getting to in production. So for data, as I already said several times, we need to version control. That's a no-brainer. Version control the code. Then a good practice is to automate data quality checks to see some ranges of the data automatically and document those expectations on the data that you might have, and to stop the pipelines if something's out of order, there's too many outliers or something like that. Then we need to design for reusable and modular data pipelines. The best practice also coming from traditional software development, where we can do data pipelines development and test data pipelines more easily if it's in modular, built in modular fashion. Of course, test feature creation and data processing code. Use feature store to ensure that we can reuse the features. We can calculate them, design them once, and reuse them across different models and teams. Adopt CI/CD for data pipelines, so that implies a lot of automation that needs to be done. You need to test and deploy automatically. And having all of this infrastructure as code helps when you need to automate things. You can do Ansible or Terraform, use here. And you need to be aware of the compliance, everybody who needs to access to which data with the GDPR, implement the deletion requirements. If someone wants their data to be deleted, you need to think about this. And training and serving skew. So that happens when we have feature engineered features in the during the training that we create those in one way, and we use let's say a different code for doing this in production. For example, if you're optimizing this code for production, then there might be some differences in this code. So and also, so you need to test for these changes if these are the same. For model best practices, again, versioning control, but also tracking experiments to know exactly what you have already tried, and that it's not scattered around in many notebooks, developers' notebooks. And you would want to probably check for each feature if it's useful enough, if its usefulness to cost ratio is high enough. You want to check all of the hyperparameters of your model and understand what each hyperparameter does, how it affects the model and performance. And the good practice also is to have a simple alternative model, such as, I don't know, linear regression or logistic regression for classification, that you can train easily and quickly, and just use it as a additional check for checking if your fancy big model is good enough, better than the simple alternative. Then testing performance on important subsets of the data. For example, your model might be okay on average on all of the data, but maybe fail on specific regions. That should also be checked. And you want to understand the real-world impact of the model outputs. So model output is just a proxy for some real-world quantity or value. So you want to know how exactly this relates to the real world. When deploying the models, it's great if you can have canary deployments. So just roll them out to a limited set of users, so that if something catastrophically breaks, you can simply fall back to the previous version. So you should also have a rollback strategy in place. And monitor for model degradation in production. So you want to know if the model predictions are still working or not. And you have to have some kind of process in place to check for this automatically. And you want to understand how fast this goes stale, so that you can retrain the model if it goes stale. And and you want to have automatic retraining pipelines, but here, so-called continuous learning. But here, there's a problem of selecting the data from the production to retrain the models on. So that's a different problem altogether. So how does finally Databricks help with all of this? So Databricks platform, Databricks Lakehouse architecture is a full, comprehensive, complete solution for data engineering and data warehousing, but also machine learning. And you can use it to ingest the data, transform the data, aggregate data, and build your machine learning models all within the same platform. So some of the features, I'll go through some of the most important features of the platform. First of all, Delta Lake is a file format, let's say, that gives you ACID transactions, which ensures data consistency and reliability. It's like a given with relational databases, but in big data world, it's not so common. So this is a big thing. Also, schema enforcement and evolution, when you are helps with, of course, data quality. When the data changes, this is covered by the platform. You have a way of handling this. Then time travel, you can always go back to previous versions of the data. So when you're doing your experimentation, you can check how well your model worked on previous versions that you used for training. Then deletes and upserts also a given with relational databases, but also in the big data world not so common. But it's also a big game changer, let's say. So it enables you to do iterative and incremental development of the features and data processing pipelines. And data skipping and other optimizations, such as liquid clustering, that's the newest one, greatly improves the performance. Next, I'd say would be Delta Live tables. This is a framework for building data processing pipelines. And you just define transformations in the form of SQL or using the API, and DLT would then manage orchestration, cluster management, monitoring, data quality. You can define expectations on the data that will be checked automatically, error handling, and all within the same framework. And it can also do CDC, change data capture, with this expression apply changes into a table from this table. CDC is also important when doing importing data. Also, let's say, a game changer if you don't have it. So this is a screenshot from a Delta Live table pipeline. So this graph of boxes is automatically constructed from your code that you use for where you define your tables, so-called live tables. And the DLT then constructs this graph and monitors the whole pipeline. It can retry different steps, and you can see checked for the errors and so on. So it's very reliable and nice way to organize data processing pipelines. Then very important is Unity Catalog, a big feature of the whole platform. It centralizes data discovery and access of tables and data sets, and also centralizes data governance and security, so you can use fine-grained access control from a central location. Also enables data lineage, so tables, columns, notebooks, workflows, and dashboards all can provide automatically collected lineage information. So you can see which notebook uses which table and column and similar things. Then it also allows for better collaboration, because many users from different projects and workspaces can use the same tables across the organization without duplicating data. So its Unity Catalog features are embedded in different places in the platform. So for example, in the Data Explorer, something let's say standard with let's say data tools, you can assign permissions on different tables. And this is an example of the lineage that you can inspect for some columns. You can see where each column came from and where it's being used, or what other transformations it's being used for. Then next we have Feature Store, which allows for centralized feature management. You can create your features once and discover them by other teams and reuse them in different other models and projects. And since Databricks runtime 13.2, any table in Unity Catalog can be a feature table. So this simplifies things a lot. And also we have lineage from Unity Catalog. It's available in Feature Store. You can see it upstream, downstream lineage. And it's consistent right across the models. So the features you create once for one model can be reused in others. And also the models, if you log your models with Feature Store's API log model, then the model will include information about the features that were used for training, and it will automatically fetch those features from the Feature Store during serving time, during production. but you have to use it consistently, use the API from Feature Store to get advantage of this feature. And finally, you can publish feature stores to online store. Amazon, it's all, mostly on Amazon, and Amazon DynamoDB is the most supported one. And then when you use Databricks model serving just creates endpoints with URLs to your models. Then model serving knows to fetch data from feature stores from these online stores. Then we have MLflow. It's an open source framework, but embedded inside the Databricks platform with some additional features available in the platform and not available in the open source version. So it's embedded throughout the platform, and it consists of four parts of the API. You have MLflow tracking that's used for logging your experiments with any metrics that were output from the model and all the parameters that were used. And it can also track the data that was used for training the model. Then we have MLflow projects and models that serve as a standard, let's say, format for packaging the models, different flavors of models such as scikit-learn or TensorFlow models. There are different flavors of these. And also for deploying models to different serving platforms, inference platforms. And finally, we have model registry. That's a central store for models and also provides the UI, web UI, where you can inspect all of your, from a central place, you can inspect all of your models, the versions, and their life cycle going to production and different stages. So this is again a screenshot showing from MLflow tracking, where pointers cannot see. So you can see the parameters that were used, metrics, and also you can inspect it gives you the example code that you can use to do inference on new data with this exact model from the model registry. And there's this button, reproduce run, and you can reproduce the notebooks, the libraries, and the code that was used for training, so you can reproduce your whole environment there. And also for model registry, we can simply search through our models, see the different versions that exist, and whether they are being served or not, and things like that. If we click on one of the models, then we can see the different versions of that model and also the stage they're in. For example, staging or production and so on. Different users can request to transition the model to different stages, and other users can then reject or approve this transition. So that's also very important here for going to production. There's also this trade-off between using central model registry and per workspace model registry. We don't have time for this, but there's also something to consider. Next is AutoML. All the platforms and machine learning platforms today offer a similar thing, where you just give it an input table, a target field, and the type of problem that you are solving, classification, regression, or forecasting, and it will generate code for you and models. And also you can specify that some of the features should be fetched and joined from the feature store. And then once you have these notebooks, you can use those models to register them to model registry right away, or you can use those notebooks as a starting point for your experiments. And finally, CI/CD integration. It's also embedded at different places in the platform. So for example, there's Databricks repos UI that you can use to check out branches, merge changes, commit and push changes. and it provides a REST API similar to other parts of the platform. It's all available through some kind of API. So this also, you can use it to, for example, automate things through Git automation or Jenkins or something else. So at different points in your pipelines, you can do automatic pushes and updates of the code. So for example, in production, you can either directly reference notebooks and code in specific Git branches, or you can set up read-only folders, and then at some point you can automatically update that code and fetch the latest changes in those folders through automation. And also MLflow model registry also provides API, so you can also use Git automation to transition models through different environments automatically. So when you are moving to production on Databricks, first of all, you need to define environments. Well, you probably need development, staging, production, maybe testing. Some people have testing environments also. So what does it mean, different environments? You can separate them by either multiple cloud accounts, or you can use multiple Databricks workspaces within a single cloud account, or you can separate the environments by access controls within a single workspace. I think the cleanest one is the second, when you separate them by workspaces. And also, when you're going to production, you have code and models. So these are two different things that might not be related to each other. They need to go to production together, probably independently. So for code, it's just the best practice from software development. You probably have a dev branch for development and specific feature branches for specific features. And then you merge those into either some testing branches where you do tests. And once it's ready for production, you either merge them to the main branch or one of the release branches. Then you can then deploy. However, this life cycle of models and the code might move independently and asynchronously. So there are different ways of moving to production. So you can either train your models on development environment, then promote the code to the staging environment, retrain there, and do the same with production. Or you can move code to train the models and move the models into next stages, or use some hybrid approach. The workflow recommended by Databricks is to, on development environment, you develop training and other code, promote the code. In the staging environment, you do test your training code on subset of the data, and test all other code, then promote code again. And then in production, you train again on the production data, test the model, and then finally deploy model and code. So I will leave you with a couple of links and resources you might want to check out. And I think I'm out of time, so thank you very much.